Okay, we're going to continue our review of right triangle trigonometry with emphasis on using the calculator. First thing we're going to want to do is grab your calculator, press the home key, and you should have this screen. Once you're on the home screen, press the numbers 5 to access setting, followed by 2 to get document settings. We want to set two things today. We're going to be rounding to the nearest thousandth a lot in this class, so you're going to want to set your calculator to do it automatically for you. So if your calculator is set in floating decimal, scroll down to get to the fixed numbers, and we're going to select fixed 3. That will round to 3 digits after the decimal point or the nearest thousandth place. Then under the angle menu, select degrees. Radian is the default measure for the calculator, so we want to make sure that that's set correctly, especially if you've gotten a new calculator or reset it at some point. Now, don't press OK yet. Press Make Default, because this will make sure that every document or scratchpad that you open is set with these settings. Then press OK. Now, we're going to utilize trigonometry to find a missing side length in a triangle. And so looking at example 1, we have a triangle in which we have a 59-degree angle, and then we have two sides labeled 5 and x. X is the leg that is adjacent to the 59-degree angle, and 5 is the leg that is opposite the 59-degree angle. Since we have both adjacent and opposite, it would be in our best interest to use a tangent ratio. Tangent, which is always followed by an angle measure, so tangent of 59 degrees equals the opposite over adjacent, which is 5 over x. That is the equation that relates those three things in the triangle. In part B, we're asked to solve that equation. The first thing that I'm going to do is to multiply through by the least common denominator. Well, there's only one denominator, so I'm going to multiply through by x in order to clear any denominators from the equation. So I get x times the tangent of 59 is equal to 5. Then to solve for x, we can divide through by the tangent of 59 to get x is equal to 5 over the tangent of 59 degrees. That is as far as we can go without a calculator, so that is our exact answer. We're going to input that to the calculator, and now we're going to get an approximate answer, which will mean that it's rounded off. So in the calculator, we'll type in a scratchpad document. So I'm going to press A to get into scratchpad, and then type in 5 over the tangent of 59 degrees. In order to do this, I'm going to press Control and then divide to get a fraction template. It's going to be in our best interest to use that in a lot of cases in this course, so get used to pressing Control and divide to get yourself a fraction, and then put 5 in the numerator, cursor down, and put tangent, which we can go to the trig menu and select tangent of 59 degrees in the denominator, press enter, and that gets us 3.004, which is our approximate answer. And that's rounded to the nearest thousandth because we already set our calculator in that mode to round to 3 digits after the decimal point. We can also use inverse trigonometric functions. Those are going to be utilized whenever we're looking for an angle in a triangle. So again, it's a right triangle. We're interested in angle A and the two side lengths that are related to angle A. 3 is the adjacent leg of the right triangle. 5 is the hypotenuse to the right triangle. So if we have both the adjacent and the hypotenuse, then we're going to use a cosine ratio. Cosine will be followed by the angle, so cosine of angle A equals the adjacent 3 over the hypotenuse 5. That is the equation that relates those three quantities. Then we're going to solve for measure of angle A. In order to solve for angle A, we need to undo the cosine. Bear in mind that cosine does not multiply angle A, and so we are not going to divide to undo it. What we're going to do to undo the cosine is we're going to use the inverse cosine function. So the measure of angle A is equal to the inverse cosine of 3/5, and this is our exact answer because we have not yet rounded it. Once we put it into the calculator, it's going to give us a rounded answer. So in the trig menu, select cosine inverse, and then type in 3/5. Press enter. It gives us 53.130 degrees, which is our answer for part C, the approximate answer. All right. On the next page, you may not be aware that degrees can be divided into smaller parts. A degree is divided into 60 smaller parts called minutes, and every minute is divided into 60 smaller parts called seconds, just as an hour can be divided into minutes and seconds, although this is different contextually because we know we're talking about an angle. So minutes and seconds refer to parts of a degree. That's typically written as follows: 25 degrees, 17 minutes, 51 seconds. It looks a lot like the notation for inches, for feet and inches, although again in context we know we're talking about an angle. For purpose of converting from degrees, minutes, and seconds into decimal form, we can use the following conversions. 1 minute is 1/60th of a degree, 1 second is 1/3600th of a degree. So to convert from DMS to degrees, we have 41 degrees plus 36/60ths of a degree. 36 minutes is 36/60ths of a degree. And then we have additionally 54 3600ths of a degree. So what we will want to do with that is to reduce these fractions if we're doing this without a calculator. 36/60 reduces by a factor of 6 to 6/10. Now I know that can reduce a bit further as well. However, 6/10 is 0.6, so at that point we can just make it into a decimal. And then 54 3600ths reduces by a factor of, let's say 9. If we reduce it by a factor of 9, we get 6/400. And then that reduces a little bit farther to 3/200. I'd love to see that third fraction with a denominator of 100, because then it's the hundredths place value. So we already know this one's 0.6. 3/200ths is 1.5 100ths. So now what we have is 41 plus 0.6 plus 0.015. Final answer, 41.615 degrees. Most of the time when you convert between degrees, minutes, seconds, and degrees, you'll do so using your calculator. So in example 4, I'll show you how that's done. So in example 4, first thing we're asked to do is to convert from degrees, minutes, and seconds into degrees. So first thing that we will do is type the degrees, minutes, seconds into the calculator. In order to do so, it will be better for us to use a template for degrees, minutes, and seconds. The template key is right next to the 9. So if you press that template key, you'll see where there's a place for degrees, minutes, and seconds. You get an empty shell there that we can fill in with the degrees, minutes, and seconds. So now type in 5, cursor over to minutes, type in 23, cursor over to seconds, and type in 57, and then press Control and enter, and we'll get a decimal value of 5.399 degrees. In part B, we're converting in the opposite direction from a decimal degree measure to degrees, minutes, and seconds, and this time we're rounding to the nearest second. So in order to do this, we just need to type in the 53 degrees, 0.278, and then we're going to convert that to, so in order to convert, we're going to use this little key over here that has a little book on it. That's also right next to that template key that we just used. And menu number 3 has what's called a conversion symbol. You're going to want to select the conversion symbol, and you get that little triangle. Now we just have to tell it what we want to convert to. So we want to convert to degrees, minutes, and seconds. Type the letters D, M, and S, and then press enter, and your calculator converts that to degrees, minutes, and seconds. So that would give us 53 degrees, 16 minutes, and 41 seconds if we're rounding. Okay, you may remember some application problems in geometry where we used Sohcahtoa to find some lengths indirectly. Here's an example of one of those types of problems. So a student is really bored in class. He is looking up at the clock. If he were looking straight ahead toward the front of the classroom, he would have a 0-degree angle of elevation to his line of sight. However, his line of sight is elevated by 23 degrees and 42 minutes. I'm going to insert a right angle in between the horizontal line of sight and the vertical wall. Other things that we know is that the student's eye level is 3.2 feet above the ground, which means that this point on the wall down to the ground is also 3.2 feet. And then we also know that the student is 10.3 feet away from the wall, which means that that horizontal line of sight is also 10.3 feet. The thing that we're looking for is how high the clock is mounted above the wall. So I'm going to put an X here on that vertical distance in between the horizontal line of sight's intersection with the wall and the clock. So we can find X using Sohcahtoa because Sohcahtoa applies to right triangles, and I have a right triangle right here. As far as that angle is concerned, X is opposite and 10.3 is adjacent, so that means that we can use tangent ratio. So the tangent of 23 degrees and 42 minutes is equal to opposite over adjacent, X over 10.3. Multiplying through by the denominator, we get X is equal to 10.3 times the tangent of 23 degrees and 42 minutes. That's not actually the answer to our problem. X is only part of the distance from the floor to the height of the clock. So in order to get the full distance, what we're looking for is this red line right here. We're just going to simply add 3.2. So the height above the wall is 10.3 tangent of 23 degrees 42 minutes plus 3.2. That's what we call our exact form answer. And then we can approximate by using the calculator. Now you can type in this entire answer into your calculator, 10.3 times, and even though I'm saying times, you don't have to type it into the calculator. You can just follow it with tangent of 23 degrees 42 minutes. We'll need the degrees and minutes template. So pull that template up, which is next to the 9 key. That's where their template key is. And then type in 23 degrees, cursor over, type in 42 minutes, and you don't need to type in the minutes. You can just leave it blank and then press enter. And our, oops, I forgot to add 3.2. So adding 3.2 to that, our height is approximately 7.721. Since all the lengths in this problem were measured in feet, that will be measured in feet also. Okay, another problem with angle of elevation. At a certain time of day, a student 5'3" tall casts a shadow that is 8 feet 4 inches long. We want to find the angle of elevation of the sun, which is between the line of sight and the horizontal. If the student is 5'3", we can actually convert that to inches because it'll be handy to have it all in one single unit. And then the shadow is 8 foot 4 inches, and we can convert that to inches as well. That's 100 inches. Since we now have the sides that are opposite and adjacent to that angle that's unknown, we can write a tangent ratio. Tangent is always followed by the angle, so tangent of x equals 63 over 100. If we want to solve for the angle measure, we need to undo the tangent. So that means x is the inverse tangent of 63 over 100. That's going to be our exact form answer. And then we can utilize the calculator to get an approximate answer. This one we want to round to the nearest minute. So x is the inverse tangent of, what was it, 63 over 100. Press enter, and we're going to need to convert that to degrees, minutes, seconds. So use the little book, pull up the conversion symbol, and then type in the letters DMS. Enter. And we're rounding in this time to the nearest minute. So that's 32 degrees, and what you'll notice is that the number of seconds is over 30 seconds, which is half a minute. So that means that 13 minutes is actually closer to this approximate answer. So our rounded answer would be 32 degrees and 13 minutes. In example 7, we have a plane that is flying at an altitude of 5.6 miles. I'm going to draw in some lines here. We'll draw in a horizontal, and a horizontal and vertical will always create a right angle. The plane's altitude is 5.6 miles above the ground, and it's approaching a runway at an angle of depression of 11 degrees and 51 minutes. What we have to be really careful of with relating to angles of depression is that if the plane is flying straight ahead, it is at 0 degrees angle of depression. So if it's flying downward, it's 11.5 or 11 degrees and 51 minutes lower than that horizontal. So it's not the angle inside the triangle. What you may notice about that is that we have two horizontal lines and we have alternate interior angles. So this angle that's inside the triangle is also 11 degrees and 51 minutes, but it's the angle down near the runway or our destination. And then the thing that we're looking for in this problem is the distance directly from the plane to the runway. So if I go directly from the plane to the runway, that's that angled distance right there. That's going to be the hypotenuse of the right triangle. 5.6 is opposite the 11 degrees and 51 minutes. So that means that we can use a sine ratio. So the sine of 11 degrees and 51 minutes is equal to opposite 5.6 over x, the hypotenuse. I'm going to multiply through by the denominator to clear any fractions. So we get x times the sine of 11 degrees 51 minutes equals 5.6. And then in order to solve for x, x is equal to 5.6 divided by sine of 11 degrees and 51 minutes. Now that is the distance from the plane to the runway. We were asked for that in exact form. And then we're asked to approximate the time of descent. In order to approximate the time of descent, we need to know how far it is that the plane is flying. So let's go ahead and get an approximation on that distance that the plane is flying in between its position now and the runway. So we need to type in that expression, which is 5.6. And to be safe, I should probably use a division template or a fraction template. That's control divide. Type in 5.6, cursor down to the denominator, and type in the sign in the trig menu. And then inside the parentheses, we're going to need the template for degrees, minutes, and seconds. And type in 11 degrees and 51 seconds. Press enter. We get 27.270. Now that's going to be in what, miles, right? Because our distances are measured in miles. We do know that the speed of the plane is 150 miles per hour. So if we're looking for time, time is distance divided by rate, which is going to be that 27.270 miles divided by the rate of 150 miles per hour. In order to be entirely accurate, I want to use the answer that's already in my calculator, because even though the calculator rounded it off for us, it still stored all the digits of that answer to its most accurate form. So I'm just going to divide that result by 150 miles per hour, and that gives us 0.182 hours. The reason that's in hours is because our rate was measured in miles per hour. The answer that they're looking for is in minutes. Now that's the type of minute in time that they're looking for. Well, if what we've got is measured in hours, then if I multiply that by 60, I should be able to get the number of minutes in time that that's equal to. So back to the calculator, multiply that result by 60, and we get about 11 minutes. And that's the approximate time of descent. Okay, we have a couple more quick examples here. For each acute angle, a trigonometric ratio is given. Sketch a corresponding right triangle. So for this first trig ratio, we're given cosine of angle A is 40 over 41. I'm going to draw a right triangle that has an acute angle A in it. Cosine is adjacent over hypotenuse. So I'm going to put those as 40 and 41. And then I'm hoping that you remember that that is a Pythagorean triple. And the missing side here is 9. So we can figure out that missing side using a Pythagorean theorem or using a Pythagorean triple to make it a little bit quicker. Then what we want is the other two trigonometric ratios. Sine of angle A is the opposite over the hypotenuse, so the 9/41. And then tangent of angle A is the opposite over the adjacent, so 9/40, and we have our answer. Last example is another acute angle J, so I'll just draw a right triangle. And acute angle J has a tangent ratio of 3. Well, now you notice that 3 is not a fraction, so I'm just going to put it over 1. And tangent is opposite over adjacent, so we can make our opposite side 3 and our adjacent side 1. Now we have to find the hypotenuse. That's not a Pythagorean triple, so we'll want to use the Pythagorean theorem to find the hypotenuse. 1 squared plus 3 squared would be 10, so that gives us a C value of the square root of 10 that we can insert there. And so now we're looking for the sine of angle J and the cosine of angle J. Sine of angle J is opposite over hypotenuse, and cosine of angle J is adjacent over hypotenuse. Now, as you look at each of these results, realize that your final answer must be rationalized, so we'll need to multiply both the top and the bottom of each of those fractions by the square root of 10 in order to rationalize that the denominator of that fraction. So sine of angle J is 3 times the square root of 10 over 10, and cosine of angle J is 1 times the square root of 10, which is just the square root of 10 over 10. And there you have it. Thanks for your attention, and have a great day.